All right, good afternoon, everyone. Hope everyone enjoyed their lunch. So what I'd like everyone to do first is imagine you are an analyst, an operations engineer, maybe at an upstream gas company that's looking at multiple rigs on multiple dashboards. Or maybe you're looking at multiple compressor systems for a midstream company and trying to understand complex questions that need to be asked about that system. Which piece of equipment, which compressor, which rig is trending towards end of use? And at exact what time does that need to be replaced or fixed? Maybe you're asking more complex questions about the interactions with that piece of equipment with environmental data, soil data, telematics, or operations and maintenance logs. Those different pieces of data come through the back end as different formats, different types of information, and present a true problem that is not just a problem for the energy industry, but it's a problem across many different industries dealing with spatial data. And that's this problem of unstructured sensor data. So unstructured sensor data is often unused. It is fragmented, it's in different storage servers, it's in different physical formats, different file types. And this is a problem across supply chain industry, across aerospace, but also in energy. And current solutions aren't really meeting this problem, especially current artificial intelligence solutions, which I'm sure many of you have heard of on the news, are not solving this problem because of these four issues. There is no-time, real-time querying of that data because the AI does not understand it. AI is only understanding language or software code, but not the numbers that are in a gigantic CSV file of sensor data. There's limited 3D visualization capability. Companies want to be able to see their data if it's representing something in real life out in the field. Implementation costs are very high to actually unite this data and to apply an AI solution on top of it. And potentially most importantly, the precision of data is actually lacking. We know that the data is coming from a physical location, but we aren't sure about the accuracy and precision of exactly where that data is being collected by that sensor. So that's why we're here. That's why CubeNexus is here. We're building the AI Decision Intelligence Suite for sensor-derived data. Ryan mentioned we're a data structuring company. That is the key differentiator that we have, that we are able to pull in many different types of data inputs and structure them in a location and time standardized format for precise spatiotemporal analysis using AI. We're building this suite so that we can build AI agents on top of this data structure, co-pilots for an analyst, for an operation engineer to sift through massive amounts of data and actually use that data to answer questions and provide insights that aren't currently being used. So why now? At the company level, we believe we're at this intersection where there is a giant amount, an enormous amount of spatial data being created every day across industries. Most of it's not being used, but now machine learning has graduated to AI ubiquity, to where it's not just machine learning algorithms that can make the most and build specific applications on these data sets, but we can actually leverage AI using human language and human voice to understand and find insights very quickly from this massive amount of data. That's what's creating this huge demand for companies like ours to do data structuring. There are many partnerships that we need in this process, of course. Data management solutions, data serving and storage solutions. But the key of being able to actually understand this different type of sensor data with AI, basically creating a language for AI to communicate with CSV files, with Excel files, with images, with LiDAR scans, is what we are doing. So here's the differentiation just visualized. Data comes in from an operational asset. You know, for a pilot, as we're talking about today, we would only want to have a very small scope, like maybe one rig, one compressor, one distillation tank, and the sensors accompanying that data. And we step in the circle in two ways. First, on the data structuring. So we say 4D structuring because we do pull the location and the time, the 3D location and the time off of that data input. Whether it's any one of these, camera, LiDAR, IoT sensor data in CSV files, telematic data in CSV files, RF data, We take the time, the location, the lat long, the depth if it's underground, the elevation if it's above ground, and we standardize that into a very simple 4-column, literally think 4 columns on an Excel spreadsheet data structure. Once we have it in that structure, we're able to do so much with it. Because of our proprietary geospatial reference system, which is cube-based, hence our name, you can kind of see it in the back of this slide, we're able to do many, many things at an efficient, affordable, and commercialized scale that current companies just can't do. So AI native, we can query it with an LLM. We can do anomaly detection, create artifacts like graphs and charts and bars in our platform very quickly. Digital twin applications, because we actually have the 3D location of that sensor data, we can very quickly create 3D representations of it. So let me just give you another example. So let's say you're on a data science team or you're a data engineer, not necessarily an operations engineer, you're actually dealing with the spreadsheets, and your CTO or a technical director asks you a question like this, like what is the impact? I did a LiDAR scan of like 5 kilometers of pipeline, and we identified a 7-centimeter crack on this pipeline, or a scratch, maybe a bird flew into it, who knows. What is the impact of that scratch on the asset valuation? Right now, that is a complex question to answer. There's many variables as to what the valuation of that 7-kilometer piece of pipeline is. Market rates, the material of the pipeline, the environment, where it is in the US, any other sensor data that's being collected. Maybe there's flow sensors or vibration or pressure sensors on that piece of pipeline that are communicating things about the real-time performance of that piece of equipment. All of those things, if they were standardized spatiotemporally, could be queried, and you could answer that question very quickly in a matter of minutes, literally, instead of however many hours it takes to pour through those Excel sheets, do that market research. The LLM already has so much of that baked into it, and we add the real-time data from your company on top of that and are able to answer that question very efficiently and accurately. So as I mentioned, this is not just an energy application. The only reason I bring this up is because my co-founder and I do have a background in aerospace. We were both in the Air Force, myself for 7 years, him for over 20 years. And so we saw this problem in real world. We saw the problem of intelligence data being collected and not being used, of an aircraft coming back with terabytes of data on it and 90% of it being thrown away, not being able to answer a question very quickly. Not being able to answer a question accurately. Analysts spending hours and hours on a problem they should be spending minutes on. So inefficient use of time, missed cost savings. And so we bring this up just to show that we have that real experience, and we want to bring it to this industry as well. So from a more practical perspective, how we make money, you saw the platform on the second slide. This is a SaaS subscription model that we have right now. There are other options that we are currently building, like those agents, like the Copilot, that could be additional, but right now it's a pretty standard annual licensing fee. And so you're probably thinking, like, there are competitors out there, right? There are companies trying to do similar things. Really, the only ones are here in the middle, some of these big players, and we really beat them on cost. And if you're not already working with a C3 or a Palantir or an Aviva or KDI, then you want to implement an AI solution in your company. Partnering with a CubeNexus to build something is a much more affordable and efficient option. These companies are charging millions and millions of dollars every year, if not more. I kind of highlight that on the second slide. Even if you just take standard alternatives, even some that are manually supported, the average cost of implementing an AI solution for a set of assets is over $400K a year, according to our research, and we could do it for around $120K. And when you see my last slide, you'll see it's even less than that for the pilot proposal. So we do have some traction, some past pilots that we've done. Effectively, for example, is a software engineering company, and they work heavily in the telecom and oil and gas industries. Commit Technologies is an aerospace drone company, so we've done some testing with them as well. And you can see the quotes, it's a little small, you might not be able to read it all, but are mostly from aerospace, but we really believe the application is real in the energy industry as well. A lot of the data that is being dealt with in the industry, whether you're midstream, upstream, or a service provider, is three-dimensionally really relevant. Where it is, either above the ground, below the ground, or in the air, is very important, and the time series nature of the data analytics is highly important as well. So just for the last couple minutes, or the last minute, we are building in Tulsa. We have an office over in Gradient. We have 5 employees, 2 relocated here. We have been part of several accelerators, including this one in the state. And Oklahoma is pretty perfect for us. There's a lot of energy companies here. We're talking with many aviation partners as well. Drone and aerospace is a huge area, and that's what we would use a grant to kind of build. This is the rest of our team. I'm actually in Chicago. My co-founder Adam is here. He's from Bixby, and then we have our lead engineer up in Boston. And then just kind of finalizing on the pilot, this is how we imagine the total cost to be for an 8-month pilot, but you can see kind of those 5 steps there. The first piece, really, we want to design partner. We want to partner and learn about a specific scopable use case that could bring value to your organization, to a data science team, or to an operations engineer, and then just identify those data sets and KPIs that would provide that value. And then after that, it's really the data pipeline being built, connecting with those different pieces of a backend, whether it's a set of folders on a shared drive or a data lake to our platform, and then we can do everything else that I mentioned before. So I'll stop there and open it for questions.
Thank you, Steven. All right, board, we're back to you guys. What questions do we have?
Just a couple questions.
I can hear you.
Better. Yeah. Close enough anyway. Just a couple questions in terms of like the special sauce, or you mentioned some proprietary IP. Is that stuff that is more just repeatable that allows you to go from a lower price point with some of the potential customers, or anything that you could elaborate on there?
Yeah, so there are huge efficiency gains in compute using our data structure. It's very simple. Like I said, it's the 3D location and time, ID descriptor value of various different data sets, and it's really the special sauces in that geospatial time series data structure that we embedded. That's what our IP is protecting. I can give you the patents if you want to look them up. That allows for us to just massively increase efficiency of the amount of data we can process. AI can compute enormous amounts of language because it's all in text, right? Or of software code because it's in a very simple, essentially, format. But a lot of sensor data collection is not in a simple format. A LiDAR file is very heavy. A picture is very heavy. CSV files, thousands of them with thousands and thousands of rows, are heavy. So we have to decompose those, and once those are decomposed, once that data is in our structure, we can actually do that querying much more efficiently and the visualization much more efficiently.
Does that affect how the data is stored in terms of the format? Are there any open standards by which you're saying, look, if regardless of the source of information, we can still conform to some kind of open standard, but your secret sauce is behind the scenes?
Correct.
Okay.
Correct. Yeah, and we can kind of translate back and forth, like back to lat long or back to different, like what the customer is collecting their data in. Correct.
Thank you.
So after you structure this data and you're holding it, do the companies get to utilize that data on their own? Do they interact with it within the CubeNexus system? Can they build their own queries off of it? How do you interact with it after it's all structured?
Yeah, so right now it's a web app interface that the enterprise would just have their own like single sign-on or MFA login to have their own instance. We're built on like a multi-tenancy. If you have any familiar with, like, each enterprise has their own server backend that is separate from other company server backends, right? And then we have individual logins for any individual that is kind of separate from those. So yes, the company could just log in with their instance of the platform, kind of like you have an Atlassian or you have another SaaS provider, and query the data. The difference is if you have an enterprise ChatGPT, you can't just throw 1,000 CSV files into ChatGPT and get anything useful, right? And ideally, this is what we would explore in a pilot, is not just manually bulk uploading thousands of files, but actually creating that connection between a Snowflake or a Databricks or like a SharePoint to actually just pull that in very easily on the back end, so every user is not having to manually upload every time.
How is the data visualized actually in the web app?
So it's basically in a voxel format. So we're not painting pretty pictures like a like a rendering software, like a Blender, but we are a nested recursive system to where we can essentially visualize data at differing levels of precision. So kind of, we can go down to sub-millimeter level if the data is that precise. But kind of think of how you have a screen that's made out of pixels, and when you get really close, you can see the pixels, but when you zoom back out, it looks like the screen. That's kind of how the visualization works. If we have very precise meter, centimeter, sub-millimeter level data, we visualize it in cubes, and they're very small. So when you kind of like zoom out, you can see like, oh, I have Bluetooth data that's transmitting through this area, and I can see it, but it's in like a cube format essentially.